This is, I mean, it's again being a problem of starting the recording. Anyway, what we will do is let me just go back to the asymptotic analysis and start from here. So anyway, I'll just briefly go through. Uh, Normally, every algorithm we have seen in the last session that we have counted the number of steps each instruction takes, and depending upon that, we have seen that there is the some algorithms takes constant time, some algorithms take linear, that is in terms of an expression it is, let's say we have, if you look at the previous algorithms, we have 3n plus 3 or 2n plus 3, the same way 2n square plus n, 2n plus 1. So the number of steps are nothing but it's represented in terms of functions. So now in this session we will talk about the asymptotic analysis. Now those functions, whatever we have seen as an example, are nothing but they represent the time in terms of n, or in terms of the size of the input. Now we have seen earlier that to measure the performance we need some tool. For example, the distance is measured in kilometers. We measure time in seconds or minutes or hours. The same way in an algorithm, to measure an algorithm, we need something known as asymptotic analysis. So this analysis, nothing but we do it in terms of, or we use mathematical notations to describe the algorithm. How the performance of the algorithm. Now the performance of the algorithm grows in with respect to the size of the input. For example, we have seen that n is the input. Now n, it can be 1, it can be 2, it can be 10, or n, the number of elements can be 1000 or 2000 lakhs also. So it depends upon the size of the input. That is, the performance of an algorithm depends upon the order of the growth or the size of the input. And it is proportional. That is, the time complexity of performance is proportional to the size of the input. That is, as the size of the input increases, the same algorithm may take a longer time to execute or complete its execution. Now let us consider we have a function f of n. Now this function f of n okay. Now let's assume it's any function f of n. Now n, let us say we are starting from 1, 2, 3. It's increasing n. So n can be 10, it can be 20, it can be 1000. As the n increases, it can be a million, 10 lakhs, or lakhs or 10 lakhs. It can be a million. Now suppose if we have a function n square plus 6n plus 5. Now this is also just like I've taken an example of a function, that is f of n is a time function. It's a time function like we have seen in the other algorithm, that is 2n square plus 2n plus 1. The same way here also we have time function. This expression has the highest degree as n square, which is a polynomial of it's a quadratic polynomial. So the expression is quadratic expression. So this is nothing, this expression, the function f of n, what we say n square plus 6n plus 5 is nothing but, let's assume that through when we counted the number of steps, we got this as the expression. Now what asymptotic analysis says is that now when we have this expression for smaller values of n, it matters. The different degrees of the polynomial matters, but we are not bothered about small values of n here. We are bothered about large values of n. Now large values of n means even if you take 1000 or 10,000, it's a large value. We are not bothered about 1, 2 or 10 or 20, because now if you just look at a real-time example. Now suppose we have might have developed a search algorithm to find search a user on Facebook. Now, are you going to search your n is going to be 10, 20? Are there only 10 or 20 Facebook users that among them you are going to search? There are millions of Facebook users. So, what we mean here by saying that when n, we are not bothered about small values of n, means that obviously when you apply the search algorithm to Facebook or to what do you call Twitter or to search a user, what happens? N is not 10 and 20, it's not small value. It is millions of users. Among them, you are trying to search a single user. So we are bothered about the large values of n. Now, when the value of n is 10,000, assume we are not bothered about 1, 2, or 10 or 20. If let's take n as 1,000. When n is 1,000, n square becomes, you all know n square, 1,000 into 1,000, n square becomes a million. Whereas 6n is 6,000 and plus 5. Now, what asymptotic analysis means is, now is plus 5 in that expression has any meaning or value when we have n square, when n is 1,000? So what it means is, for 10 lakhs, if you just add 5, it doesn't matter. Value is not going to affect that much. It's negligible. 5 adding 5 or the expression plus 5 is negligible. Not only 5, when we have 6 and 6,000, let's say, adding it to, when n is 1,000, adding it to 10 lakhs or a million, I would say adding 6,000 to a million also is not, I mean, it's insignificant there. It doesn't make much difference. So adding 5, adding 6,000, it's insignificant when the value of n is very large. And this is, we are talking about 10,000, we are talking about 1,000 itself. If you take in 10,000 or more than 10,000, then obviously those 6n plus 5 is not, I mean, make any difference when we have n square in the expression. So we say that the lower degree terms are insignificant. Doesn't make much difference. Now, what actually asymptotic means is not exactly a value, but asymptotic in general sense or in English term means approaching a value. It's not exactly a value. Asymptotic means approaching a value. So all the performance analysis, what we do in terms of time or even for space complexity, what we said is, we said it is an estimate. It's not an exact. So that is what is the estimate. Here we are calling that as asymptotic. So when we have an expression n square plus 6n plus 5, and when n is large, when n is small, then obviously 6n plus 5 makes a difference. But when n is large, the value or the component 6n plus 5, the lower degree components of n, doesn't make the difference. It's insignificant in terms of higher degree of n. So asymptotic means approaching a value. So now we can say that in terms of asymptotic analysis, we can say that the function f of n, which is n square plus 6n plus 5, we can say that is said to be asymptotically equivalent to n square. We are not saying exactly equal to n square. F of n is n square plus 6n plus 5. 6n plus 5 is there in f of n. But we say that f of n is asymptotically equivalent to n square. So asymptotic means approaching value. Now, once if you have this thing clear, then we can move forward. So always remember that we are bothered only about higher values of n, not with respect to smaller values of n. Now, the next thing what we're going to see is let us take an example before we go formally describe the asymptotic notations. Let us look at an example. Now I'm trying to search a number among these numbers. I have taken these numbers into an array because that is what is my collection. Now, to search a number, what do? I start with the first element. I'll check whether it is there or not. Go to the second element, check whether it is there or not. Third, so on, for till the last element, until and unless I find that element or that element is not present in my collection. So this, if there are n, this 4, if there are n number of elements, I search each one till the last nth index. That is n number of elements I search. Now here, let us consider search element is 84 itself. Search element is 84. It's the key I'm trying to search. The element I'm trying to search is 84. I'll start from the first element. I found the element in my collection. I found 84 is okay. It's found. It's true. Now, do I have to search the entire rest of the array or the elements? There is no need for me to search. So I started from the first element. I found that first element in the collection. I'm just performing a simple search here. And I'm not writing a complex algorithm. I'm trying to do simple search. So my searching, my key is 84. I'm trying to search for 84. 84, I start from the first element. I found 84. Once I find 84 element or whatever I'm trying to search, I don't have to search the rest of the elements because I already found those. So this is known as the best case. So any algorithm will have three things. First one is the best case. Then suppose if I have to find element 15 or p in this case, an example I'm saying 15 or 100. Now I have to use the same procedure, that is starting from the first element. I have 84, but my key is 15 or 100. Anyone, let's take 15. So I don't, first it's not the first element, so I have to now search the rest of the elements. Now, rest of the elements means what? Every other element until unless I find the element 15. Here I have the element 15 as the last element. So I have to search the entire array. Now here there are only 4 elements, but suppose if you have n number of elements, you have to search all the n number of elements. So 15, I found it the last position. Now suppose it was 100 I'm trying to search. So I have to go to the last element and I have to say it's not found. 15 is as the last element, so it's saying found. But if it is 100, I don't have that element. So I go to the last element and then I say that it's not found. So this is known as the worst case. That is, and remember, algorithm is same, searching an element. So first was the best case where we found the element as the first element itself. So there was no need to search for the rest of the elements. Then 15, the last element, or the element is not found. That's known as the worst case. And the third case is the average case. Let us say 21. No, though I'm just for an example taking 21. Even 47 can be an average case, or 96 can also be an average case. Average case actually is very difficult to predict. So let us say the middle element 21 itself. So what I have to do? I have to start from the first element, go till the middle element, and then I found it. I don't have to search for the rest of the other elements now. So what I say is, I say that this is an average case. And remember, average case is very difficult to predict. Anyways, every algorithm, we have best case, worst case, and average case. So we have seen taking an example. Now let us look at another example. Okay, best case. There is the other example. Okay, let us take another example. I have the number of elements, but here my algorithm is not to search. My algorithm is to find the sum of these numbers. So I have 4 or 5 numbers here. I want to find sum. If there are n numbers, then obviously I have to find the sum of all n numbers in the collection. I have taken this in an array. So what do we have to do here? Start from the first element, go to the second element, add that element, third element, add all the elements. Now, here, what do you think will be the best case? See, in searching, if it was the first element, whatever key we are trying to find, if that is the first element, then we said that we found at the first instance that we found there is no need to search all the other elements. And that's the best case. But what about best case in this scenario? That is an algorithm to sum n numbers. Anybody has any, discussion? Now here, the best case, we can't just, we have to add all the elements. So it's not that we only have to add the first element or the second element. Obviously, we have to traverse the entire array. We have to visit all the n number of elements. So if you, remember the previous example, worst case was traversing till the end, whether the element might be found or not. Here also, we have to traverse till the end. So traversing till the end of traversing all the elements of the array is nothing but a worst case. So in this scenario, when sum of n numbers are there, the best and the worst case are same. They are same. So we don't say this is a worst case. There is a best case here, and there's something else as worst case. So some algorithm or some solutions, some solutions for any problem, we may have best and the worst case are same. That in the scenario you have seen, best and the worst case are same here, and there is no average case as such, because we don't. When I say sum of n numbers, it means I don't add only 3 numbers till 27 element 21 average. No, I'm saying sum of n number, so I have to multiply all the numbers. So there is no such thing called average case here, and best and the worst case are same. So okay, anyway, let's go back to okay. Now the best case was what we call is the lower bound. That is, at the first instance itself we found the answer. Worst case is the upper bound. We have to go till the end, till the maximum elements we had in our example, I'm telling. Then the average case, we call it as the tight bound. So best case is lower bound, worst case is the upper bound, and average case is the tight bound. Now, nobody is bothered about the best case of an algorithm. You know that if an algorithm can work in worst case, obviously even in best case it can work. So we are not bothered about the lower bound or the best case of an algorithm. We are bothered about the upper bound or how the algorithm performs in worst case. Because if it can perform in worst case, then obviously it can perform in best case. So worst case, so we are bothered about the performance of an algorithm in worst case, or we are bothered about worst case performance of an algorithm, that is the upper bound of the algorithm. Now this is the example we have already seen. Let us come to the actual asymptotic notations. So here for an algorithm, in terms of performance, we have best case analysis, worst case analysis, and the third one is the average case analysis, or lower bound, upper bound, and tight bound. Anyways, the performance in the time complexity, or what we say as asymptotic notations for performance of an algorithm, we have is the term known as big O notation, big omega notation, and big theta notation. Now these are mathematical, expressed in mathematical terms, Big O notation is f of n less than equal to Cg of n for n greater than equal to 0. Don't worry about this. This equation, it seems to be very complex, but they are easy. We will solve them later in the coming slides. In the same way, big omega notation is the only difference is big O, f of n is less than equal to. Big omega, f of n is greater than equal to. That is the only difference between O notation or omega notation. Then the third theta notation is nothing but both, including O big O and omega. So if you see here, you have f of n. F of n is less than is your big omega notation. F of n, sorry, f of n is greater than C of g of n. F of n is greater than equal to Cg of n, or in the other words, Cg of n is less than f of n. And here we have C, but here we say C1 or C dash, and omega, this side is omega, f of n is less than C double dash or C2 g of n, we say. So these C1, C2 or C dash, C double dash are two different constants. Even here C is constant, and f of n is a function. We have seen what that function is. So function, it can be 2n square plus 2n plus 3 or 3n plus 3, 2n plus 3, any in terms of n, f of n function. We will talk about g of n function. So this is the mathematical notations, and these are the actual or formal definitions of big O, big omega, and big theta notations. Now let us go into depth and details, and let us see what these notations are and how these notations work. We will take up first the big O notation. Big O notation. This is the asymptotic notation we call big O. Now let us plot a function. Now on x-axis we have input, that is n, and on y-axis we have running time. So what we say is, we say that we have a function f of n plotted in such a way that this f of n function, it's coming from the number of steps we counted. This f of n function, we said that this function grows, the performance grows as the input size grows. So that is what input size is n. So as the input size is growing, even the function is growing. Function is growing. That is the performance. This function is growing means on y-axis we have running time. That is, it takes more time. Now we will say that there is another function, c g of n. Now c is constant here, g of n is a function. So what the big O notation says is that we have a function f of n, and this function f of n, and we have another function g of n. This function f of n is less than equal to, that is, it is less than equal to. Now here it might be greater than the g of n function, but f of n function, here you can see this function f of n is less than equal to c g of n function, that is this red line, for some n greater than, here it is lesser, f of n is more, c g of n is smaller. But from at some point of time, when n0, when n is greater than n0, this is n0, when n is greater than this side, on your towards your right side, n, then f of n will always be smaller than g of f of n. Obviously, you can say it is smaller. Now let us prove this. What this means. Now c is constant. C over here is constant. This constant has to be always greater than 0. I'm not saying greater than equal to. If it is equal to 0, mean whatever function g of n is, it will be 0. And 0 f of n less than 0 means doesn't make any sense. There is no function. There is no time complexity, or time measurement cannot be in negative form. So c is always, it's a constant, always greater than equal to 0. And n0 will always be greater than equal to 1. N0 is nothing but n. At some value we are saying, on the x-axis, which is x-axis is n, number of input. So n0 is itself is n, but some value greater than at that scale, on that scale. Now here n0 will always be, or n will always be greater than or equal to 1. Now you know, we have talked why c is greater than 0. It's not equal to. If it is equal to means whatever function you have g of n will become 0. C is always greater than 0. N0 or input n is greater than equal to 1. And always it is greater than equal to 1. Why? Because n is the input. So n0 will also be an input. And for an algorithm, we should have an input. At least one input, or with. You cannot say 0. You cannot say input can be 0. It should have some input. Some input in terms of n. At least one element should be there to do something, some work. So n0 or n is always greater than equal to 1. Now let us look at the definition. What we say is big O notation, that is over here, f of n is equal to O, big O of g of n, when f of n is less than equal to c of g of n, where c is a constant greater than 0 for n greater than equal to n0, where n0 will be greater than equal to 1. If this is true, then we say that f of n is asymptotically equal to big O of g of n. This equal to sign is nothing but asymptotically equal to big O of g of n, or we can say that, simply say that, instead of asymptotically equal to, because asymptotic means big O is asymptotic notation itself. So instead of saying asymptotically, we can also say that f of n is nothing but it's equal to big O of g of n. And then let us take an example. Let us say that we have a function f of n as, let's say, 5n plus 4. This is a function. Now where is this 5n plus 4 coming from? Because till now we were just saying f of n. What is f of n? It's a time function. What is that function? Time function. 5n plus 4 means what? It means the algorithm. The number of steps in an algorithm, the number of times those steps executes is 5n plus 4 times. So the time complexity we have measured in terms of, we have counted the number of steps there, and we are saying that f of n, there is a function or an algorithm which takes 5n plus 4 times the instructions are executed. Now we need a function g of n. Now remember, when g of n should be of the same degree of f of n. Now we can't say that it should be a same degree, but let us say that g of n doesn't need to have any constant. It doesn't need to have any constants. Now we will talk about that same degree later. We'll come to that because it will be confusing right now. So let us say that we have g of n as n. And remember this, we have c of g of n for this expression, that is f of n less than equal to c g of n. Now right now we are just saying what is f of n, what is g of n. Now g of n will not have any constants like how f of n has plus 4 plus 3 or whatever it is, plus 4, this is a constant. G of n will not have a constant. Now what we need to do is we need to find values, or we need to satisfy or satisfy this equation, that is f of n less than equal to c of g of n. Now here f of n is 5n plus 4. 5n plus 4 should be less than equal to c of g of n. G of n is n, we are saying. And remember, it doesn't have any constants. N. C of n. C multiplied by n. So g of n is n. So c multiplied by n. Now what we need to do? We need to find this constant, c, such that this expression becomes is satisfied. So here n should be greater than equal to n0. Remember that is what is in the function. That is this f of n less than equal to c of g of n is for n greater than equal to n0. Let us take the value of c as 6. Now it is not always that 6. 6 is one of the values which satisfies. So I have taken 6. So what we have is 5n plus 4 less than equal to 6n we have. Now for n, which value of n? N0, we are saying n0 is greater than equal to 1. So which value of n0 does this equation satisfy? You can see that if we take n0 as 1, it will be 5 plus 4. So it will be just 9 less than equal to 6. N is 1, 6 doesn't satisfy. So for n0 is greater than equal to 4, it satisfies because this becomes 20 plus 4, 24 into 6 multiplied by 4 is 24. So this is 24 less than equal to 24 is true. So what we are trying to do here is we are trying to solve this f of n is less than c of g of n, where n greater than equal to n0. This equation we are trying to solve it when we have f of n as 4n plus 5 and g of n as n. So what actually we are trying to find is we are trying to find the value of c and value of n0. So when c is greater than 0, here in this case c is 6, so it satisfies, and n0. So from here, if n0 is above or equal to 4, then we say that this equation is satisfied. So what we are going to say, f of n, f of n 5n plus 4 less than equal to c of n, where c is 7, will it satisfy? Yes. It satisfies if c is 7 when n0 is greater than equal to 2. So these are only some of the possibilities. There may be infinite possibilities of c and n0. So what we have taken is we have taken one c value as 6. So when n0 is 4 greater than equal to 4 and c is 6, then the equation satisfies. When c is 7, n0 is greater than equal to 2, this equation satisfied. You yourself can solve and see. It's satisfied. It's 10 plus 4, 14. 14 is less than equal to 14 is true. So what we are saying, this is we have to find some constant c and some constant n0. Oh, sorry, some value, some constant c and some value for n0 greater than equal to some value to satisfy the equation. Now, I told you about the degree. That is f of n is 5n plus 4, g of n is n. I said that the degree, there's a polynomial, degree of the polynomial, what it should be. Now let us consider g of n as n squared. Earlier we have taken for n, now g of n squared, n cube. What will happen now? Whatever you take the value, because it is f of n is less than equal to c of g of n. So g of n cannot have a constant, that is n plus some constant cannot have a constant, and the degree, whatever degree it might have, greater than equal to the degree of f of n will satisfy. So we cannot choose a function g of n lower than the degree of f of n. So for you can look at the degree f of n is n square, and g of n is n square. You can compute yourself. You can find the answer. For c, you have to compute. Take any arbitrary value of c which should be greater than 0, and n0 should satisfy. And you can see that for g of n also n squared, you can see that the function f of n will always be less than. So what we call is, when we say f of n is 5n plus 4 and g of n is whether it is n or n square or n cube, it will always be, f of n will always be less than equal to g of n. And if it is so for some value of c and n0, then we say that the function f of n is big O of g of n. So here, for this case, 5n plus 4. So when f of n is 5n plus 4, we can say that it is asymptotically, or we can say that it is equivalent to big O of n. If we have the function f of n as, suppose, let's say, but suppose if we say 5n square plus 4n plus 5, then when we have 5n square plus 4n plus 5, we say that it is equal to big O of n square. Why n square? Because the highest polynomial of f of n is taken, because that is what will satisfy the equation less than equal to c of g of n. So just as a formal definition, this inequality, this f of n less than equal to c of g of n for n greater than equal to L0. Let's say it's greater than 0 and n0 is greater than 1 is known as big O notation, or f of n is asymptotically equal to big O of g of n. And you can take any equation as well for f of n, and anything for g of n. G of n should not have a constant, but the degree cannot be less than, it should be equivalent to, first try with equal to, then the greater degrees. This will always satisfy. Now, obviously, it's for higher values of n, we say. So this is known as the upper bound. Big O notation is known as the upper bound because your function f of n cannot go beyond cg of n function. So this is known as the upper bound. Now just remember, big O is for upper bound, so that it will be easy for us to represent when we talk about best case, worst case, and average case. So big O is for upper bound. That computes the upper bound. Now let us take another function f of n. This we are talking about big O itself, f of n. Now what this f of n is, we have a value something as 5n square n power 4 plus 3n cube plus 2n square plus 4n plus 1. Now directly looking at this, we can say that this f of n, what is the highest degree here? It is n square. When f of n is n square, g of n can be n square or more than that. But since f of n is less than or equal to c of g of n, we say that asymptotically f of n, that is 5n power 4 plus 3n power cube, highest polynomial is, or highest degree is n power 4. So we can simply say that f of n is equal to O of n power 4. There is no need for you to compute all that, solve all that. Solving what I shown you is just for your understanding. But whatever it is, the highest degree will, come into picture. That is what we are saying here is n power 4 is the highest degree. So in asymptotic analysis, what we say that this highest degree is significant. Rest of the other components of the equation, n cube, n square, n 1, all these are insignificant. They have no significance to the higher order or to the higher power of n as the size of n increases. So directly by looking at the equation, you can say that f of n is big O of n power 4. Then suppose if I have this n cube plus 10 n log n. Now is n log n smaller than n cube or greater than n cube? What is the degree of n over here? Degree of n in n log n is 1. N power 1. That is what is n. So n cube is always going to be higher than n log n. So what is the highest degree here? N cube. So we can say that f of n is O of, or big O of n cube, because this component 10 n log n plus 5 will have no significance. It is insignificant. Let us take another example. 2 power n plus 2. And n plus 2 is the power of 2. This is exponential. So what do we have here? We can directly, because there is only one component, 2 power n plus 2. So plus 2 is nothing but doesn't have any significance, because n plus n 2 power n or 2 power n plus 2 doesn't make any sense. I mean, it's insignificant. It's equivalent to n 2 power n. So we say that f of n is O, or big O, of 2 power n. So this was all about the asymptotic analysis of big O notation. Now, we have to complete the other two notations, that is big omega notation as well as big theta notation. And these topics take some time. We cannot just rush through them. So what we are going to do is we are going to take up some equations in terms of f of n, and look at the other two notations, that is big omega notation as well as big theta notation. Now, so that's all we have for today for this session. Just let me know if you have any doubts, or else we can log off and we'll continue in the next session. So if you don't have any doubts, just you can log out.